So yeah, it's my pleasure, everyone, to introduce Caterina Doglioni, who'll be giving today's seminar. So like me, Caterina's a particle physicist who works on the ATLAS experiment at the Large Hadron Collider with specific expertise ranging across various different types of physics that we like to investigate, such as the features of the strong interaction and what the nature of dark matter might be. Our astrophysics colleagues have discovered dark matter. We try to find out what it is. Now, of particular relevance to this seminar is that the experiment we work on produces a lot of data, and I'm sure Caterina will go into the details of this, but it produces so much data that we can't actually store it all to disk and then analyze it later, right? So what Caterina does, right, in her research is to develop new methods of analyzing that data in real time, right, so that we can look at all of it instead of just a small fraction, and has really been pioneering this area of real-time data analysis at the ATLAS experiment for the last 5 years, right? So I think a lot of the techniques that Caterina uses to exploit the data in this way will be of interest to many of you in this seminar. So I'll hand over to Caterina now. Caterina joined the University of Manchester in September and is one of our valued members. So I'll hand over to her, and she'll take you through what she's working on at the LHC.
Thank you very much for the nice introduction, and thanks again for the invitation. And in the seminar, I'll try to convince you that we need to make the most of high energy physics data. And you might think, well, there's so much data, you could just save a bit of it, but no, we actually want all of it, or at least as much as we can, because generating data is not necessarily cheap, and analyzing data needs to be as efficient as possible. So for that, we use real-time analysis and a little bit of artificial intelligence, but I will not talk about this too much in the seminar. We can chat about it in a different date. So, as Andy said, we use big tools for high energy physics, so I'll show you a bit about that, and then tell you how we handle large amounts of LHC data. LHC is the Large Hadron Collider. This is the collider of protons that we are getting the data from, and why we have to discard most of it. It just doesn't fit. How do we do? We take more data with less resources. This is real-time analysis, and I will tell you how we use real-time analysis for dark matter physics, and then I conclude with an idea of collaborative efforts on real-time analysis. So one thing, because I'm sharing the screen, I cannot see the chat. So if you want to ask me questions, I don't know if you ask questions at the end, wave or unmute yourself if you want to ask me during the talk, because I will not be able to see the chat. So the one slide intro for particle physics is that we are actually studying the nature and the behavior of the smallest constituents of matter. So we're going to 10 to the minus 16 centimeters roughly with respect to the centimeter level objects that we know. We're studying the constituents of protons and neutrons. These are the quarks. We're studying the most fundamental particles in the sense that we haven't been able to break them yet. So electrons belong to that category as well. And over the years, particle physics have built what's called the standard model of particle physics that describes all the known matters in terms of fundamental particles and forces. You might remember now it's 10 years ago. It's not a new discovery anymore. It's relatively new because it was a big discovery, the Higgs boson, this particle that explains how many of the massive particles in the standard model get their mass. On the other hand, the standard model does not explain everything that we see. There's a number of unexplained observations in our universe, and what we call dark matter is one of them. There's something that does not belong to the standard model, but is out there. And I will talk about that more later. So the Higgs boson was discovered, and this is one of the graphs that you might have seen in either popular science or less popular science. And you see that on the y-axis we're having events, and this is how many collision events we record that have content that could be compatible with the Higgs boson. We don't actually know which event contains a Higgs boson. So that's why we do statistical analysis. For example, here we're plotting this histogram as a function of the combined mass of the decay products of the Higgs boson on the x-axis, and then we're trying to see if there's an excess with respect to the known particles that we know produce the same final state. So there's the Higgs boson decays into 2 photons. This is what we're trying to find. This is our signal. But there's a lot of background. That is anything else that makes 2 photons. And you see this little bump here. This little bump is the manifestation of this excess, is the manifestation of the Higgs boson. And it's this bump is centered around the mass of the Higgs boson. So what does it take to make this plot? It takes a particle collider. So this is the Large Hadron Collider. There's roughly 600,000 collisions per second, but only 1 in 10 to the 13 of these collisions may produce a Higgs boson. So it's very rare to find something like this. You need to be able to select and precisely measure particles. For example, these are photon particles. These are the messengers of light, these particles, the photons. And you need a detector that is able to distinguish what photon is and reconstruct it and tell you how much energy they have so that you can go back to the mass of the Higgs boson. So these detectors are called ATLAS, CMS, and LHCb. The ones that at least there's another one, there's a few more, but these are the sort of more general purpose ones. And there's also millions of readout channels for each of these detectors. So you can imagine that it's not just a matter of the data produced, the number of events produced, it's also a matter of how much information is coming to you. So you need a lot of teams that operate the detector, reconstruct and calibrate particles, and do the data analysis. So this is our Large Hadron Collider. This yellow line here, it's actually 100 meters underground. It's 27 kilometers of circumference. And whenever there's 2 proton beams that go in opposite directions, and then in correspondence of the experiments, they actually collide. And this is where we record the products of the collisions. Now we're just beginning what is called the run 3, the 3rd data taking period of the Large Hadron Collider. So it's a very exciting time in Geneva and also here, because a lot of the things that we do remotely. And I will just show you a quick video. I hope that you don't hear the sound. You shouldn't, in principle. I will hear the sound. But so this is how we how it looks like if you go underground. There's these 4 experiments in 4 tunnels, and then there's a big LHC tunnel that is this 27 kilometer circumference. And I work on the ATLAS experiment, and the University of Manchester is also involved in the LHCb experiment. So the protons happily travel up very, very close to the speed of light, and then they collide inside these big machines, these big detectors. And this is what happens when 2 protons collide, because they're not fundamental particles. They spray out a number of other particles, and the signals, these are signals that get digitized, and then 600 times per second, they can produce a signal in the detector. So what do you do with this? Well, generally only 1 in a million collisions is of interest. So you have a system that is called the trigger system that we'll see next. And that's a system that is responsible for making choices about what is taken and what is discarded. So the first pass is fast electronics. So there's only 1 out of 10,000 events. And then it passes this still very large number of events to the second selection. That is a farm. That's a computer farm. It's called the high-level trigger. So it's software. And here you can assemble more of the information, and there's a number of cores that select only 1 out of 100 of the remaining events, and then sends it through. And where does it sends it to various computer sites around the world, and one of them is the University of Manchester. So there's a distributed data analysis also that is that's an aspect of what we do, but I'm not necessarily going to talk about this. Let's be happy that at this point we have recorded the data that we wanted, and it's going to go to it's going to be ready for analysis. Now the big problem is that we have to discard 99.9% of the data. So what if we wanted some of it, and we were interested in some of it? So some terminology that you might I will use in a little bit. So LHC data, so we need discovery. For discovery, we need the data. And this is a graph that, don't worry too much about the units, but it shows you the speed of data collection. So in 2010, when we turned on the LHC, we had this little curve that collected not very much, what we call integrated luminosity, not very much data. You had to magnify by 50. compared to how much and how fast we recorded data in 2018 when we on the last period of what we call round 2. So it's not it's true that there's always more data. We always get better at getting data out of the Large Hadron Collider. There's also another aspect that is the center of mass energy. So the more energy, the more massive particles you can discover. So without going to the particle physics details, think about E equals mc squared. The more energy you put into the collision of 2 protons, you can convert that in mass of bigger particles that we have not been able to see in the lab before because we didn't have enough energy. So that's kind of the game we're playing. We're trying to make massive particles that we hadn't seen before and detect them and add them to the standard model potentially. And then I was saying the luminosity is proportional to more data, and more data means more chances to see something that is rare. You need to collect a lot of collision events to find one that contains a Higgs boson. So this is a picture of the Atlas detector. So it's really large. It has more than 100 million electronic channels. You see that if 2 people stood on it, they would be very small. And it's as large as the Notre Dame Cathedral. It's very complex, so many sub-detectors, all these names down there, are used to measure different properties of different particles because you want to distinguish in this spray of particles coming from the collision what is what. Then you combine the information in all the sub-detectors in a process that's called the reconstruction. And then we as experimental physicists, we analyze the collection of the events that we record. And again, one event is one product of 2 protons colliding to first order. We also have to worry about good data because in some cases, it's an apparatus, it's an instrumental apparatus, some things can go wrong. So chunks of data might be not usable. And this is, for example, a transient noise problem. And this is where we're starting to use quite intensely supervised learning because you can label good and bad data and then you train it. You just give we're doing it mostly with a human because that's an interesting sociological aspect. We don't really trust, in this case, algorithms as much. We always want a human to decide if data is good or bad at some point. So at the moment, the algorithms that are running, that either supervised or unsupervised learning, where you find anomalies, are informing the decision of a human somewhere that decides where the data is good or the data is bad. So there's a simple example, I'm taking it from LHCb, where you use a BPT, and there's a lot of more complex use cases and algorithms. But this is the direction in which a lot of people are working with artificial intelligence. So data handling and analysis is the center of the topic of this talk. So I'll run you through how we do this, how we process data. So you have the collision, that's the top left figure. I don't know if you can see my mouse, but I'm circling around it. Then this gets seen by this giant digital camera that is the Atlas detector. Then at that point, this trigger system needs to select what events are kept and which events are not kept. And this is what we call up to here, it's online. It's as close as possible to when the collision happened. And here you don't, until this point, you really don't have too much time to make a decision because you have a lot of events coming through. And then after this, you can be relaxed a bit about latency and timing because you have recorded events, you can manage them, you can reconstruct them again, you can analyze them later. Because there's many channels, many features and complex data, one can use machine learning techniques at all stages. I'm giving you some examples because this is not necessarily the topic of this talk, but you might want to simulate physics processes and detectors fast and with sufficient accuracy. Machine learning can help that there. You can select events in real time. This is the trigger system. By having trained an algorithm tells you, I want this kind of events instead of this other kind of events. So you just do the inference on the trigger and you don't have to, it's much quicker than having to reconstruct and decide every time. There's also the reconstruction and classification of physics objects from low-level inputs. If you can think about the idea of this detector being a digital camera, you can also think about image recognition, and that's also another direction in which people are going to. And then in terms of data analysis, there's a lot of techniques to improve signal extraction using all the variables that we have. And there is this group that's called the Inter-Experimental Machine Learning Working Group that is now full of people, and there's a lot of interest in CERN. It's even more than the 2018 quote that I have there. So in terms of why do we use machine learning, there's an interesting aspect that this point that was made in an article or a review that is not too new about machine learning. And then unfortunately I have to stop talking about machine learning. I'll go into trigger. This table shows the effect of machine learning on the discovery and study of the Higgs boson at the beginning of the data collection. So this is something that has happened until 2016. Now there's more simplifying technique, but there's also more data. So these numbers are not necessarily the same. But in case of the discovery of the Higgs boson, you can compare the sensitivity of discovering something with or without machine learning. And you discover it faster with machine learning, which means that if you hadn't had machine learning, you would have had to collect additional data. You would have gotten to the same place. But I think the point here is that more advanced techniques for data selection are equivalent to collecting more data. And data is expensive to produce or collect and to store. So the perspective that I'm going through in terms of machine learning, but also in terms of triggering, is that we need to make the most of the data that we have. Because this collider is, we're lucky to be running it and taking data out of it. This is something that has taken 20 years to build and runs for another 20 years. And the next one will have a similarly long period of building. And then it will be, you just turn it on once. I think that's the point. So you want to make the most of the data that you have. So the big question, if more data is good, why do we have to throw it away? And here I will talk a bit about the trigger system. This is a classic big science problem. There's too much data. The signals that we're looking for are rare, so we need an enormous amount of collisions to produce any of the signals. The problem is that in all these collisions, you produce also backgrounds to the signals, and in many cases, the backgrounds look the same as the signals. So you can't really get away with, I select only the signal because there's a good filtering. In some cases, you don't have that chance. And the backgrounds are much larger. And if you run the numbers, because we have up to 30 million proton-proton collisions per second and about 1 to 1.5 megabytes of data per collision event, if you include the raw data, you're going to take 400,000 petabytes a year of data. Now, sure, it's small fish with respect to Facebook, but there's also less money involved in an experiment like this. So we absolutely need to be efficient and to be realistic on what we can take. And so we need to select interesting events in real time in the order of milli or microseconds. So this is the diagram that I showed you before. So what we call the hardware trigger, the one that is this set of boards that decides on the spot whether the events gets passed forward or not, needs to reduce the output from 30 megahertz to 100 kilohertz. And then software trigger needs to reduce it 100 times as well. So at this point, we get into a Venn diagram of problems because the data that I like for my maybe discoveries, the data that someone else likes, are not exactly the same because there's a lot of different possibilities. Maybe someone likes the Higgs boson, someone likes dark matter, and they look different in the detector. And we cannot even record all the data that I like because what we can record in full after the trigger is a small subset of that. There's also some data that nobody likes, and this may be an interesting aside if we have a coffee at some point, because even in there could be something interesting. But the point is that the data produced by the LHC is a huge amount, and we can't make everyone completely happy because we have a trigger menu. So it's like a menu in a restaurant. We decide in advance what we are going to present to feed to the analyzers of the collaboration. So when you're talking about here, single leptons is saying, do we want to record all the events that contain one muon or one electron? And is it more energetic or less energetic? And all of this has to fit. You can't record all the leptons ever, because at that point, you will not be able to record any photons, for example, and vice versa. So you have to make choices. And these choices need to be made more or less in advance, because then you can keep the data taking rates constant and everything works, your infrastructure works. It's more or less flexible to adjustments, but it does follow priorities dictated by the experiment's physics strategy. So it's not 100% Higgs boson or not 100% dark matter, it could be a bit of both. And there's also machine learning in it for the identification and selection of the particles. So this works that you're throwing away most of the data, because in most cases we don't care about all of the data that comes out of the LHC. And I'll try to explain to you from this diagram. And so on the y-axis, there is this quantity called the cross-section. So this is proportional to how many collision events will contain this physics process. And the physics process is on the x-axis. And the physics process is, this is roughly ordered in terms of how much energy you need to produce something like this. And you see that this is a log-log scale with many orders of magnitude. So we really don't care about taking all of the LHC data. We start caring maybe about, here when there's one event every 10 to the 5. So we can afford discarding one event 10 to the 5. But news, the physics they like is around here, is in this kind of segmented part. The dark matter physics I like is here. So it doesn't work for me. It doesn't work to discard one event every 10,000, to keep only one event every 10,000. Because we could be missing something in those events that we throw away. Because if we're looking only on the spotlight of the trigger, what is triggered, what about all the data that we don't have, that we've thrown out? And this is also another point. What's interesting to at the LHC is interesting. Different experiments have different interests. So for example, what's interesting, the rare processes that are interesting to ATLAS and CMS are many orders of magnitude lower in terms of occurrence with respect to what is interesting to the LHCb experiment. And the definition of interesting changes, and especially if you have rare signal processes that are buried in high rate backgrounds, you discard those. So the limitations to record more data come from a variety of technological questions. First of all, the detector readout that reads out the data to the hardware trigger. In most cases, at least and not until this coming run, no experiment was able to read everything, every single collision of those 30 megahertz or 40 megahertz. They had to anyway discard, not keep some of them. And this is changing. It's changing for run 3 for 2 of the experiments, but it's generally a hardware issue. And the same with the hardware trigger is also another kind of hardware issue. If you could make faster electronic and more efficient electronic, you can, but it takes a long time and a lot of effort. So this is something that will come later on. Then the other, the two limitations that I will be trying to avoid with real-time analysis are the CPU, because it's costly to process events at in the trigger farm, but it's also costly to reconstruct and calibrate these events in terms of CPU. So you can't take them all. But also the disk and tape store events is something that is expensive. We can't store all the events because we don't have enough disk. So the main take home for this talk is that we at U of M and also many collaborators around the world, we're trying to overcome these limitations so that we can make the most of the upcoming data for run 3. So here I will just defer this, the discussion of the detector readout and the hardware trigger limitations to another seminar, because this is something that other people also at U of M do in particle physics. They work on this kind of things. There's also another aside that is more about machine learning. I could talk about that for a long time, but not now. It's there's a problem of triggering and deciding to keep only what we know about and what we expect. So this is another direction that we're going in, is unsupervised learning, anomaly detection, learn the standard model and then find out and trigger on what's new. Complicated, not yet there, but we're starting. And I will talk more about the CPU limits for processing events. And on the left-hand side, we have a total CPU budget, and there's consumers that are different in different terms of different physics objects. So reconstructing an electron or photon is more expensive than, for example, reconstructing a muon. And on the right-hand side, you see a practical problem on the data storage. This is an estimate that was made in, I think, a year ago. It is dominated by simulation, but everything helps. You really need to keep down the amount of disk that you use, because here on the y-axis is the disk storage in, and on the y-axis is the year of running. If you estimate how much data we're going to take and don't do anything about the data model, or if we keep taking data until now, in about 2027, when we have the big upgrade of the accelerator, we're going to go over budget and way over budget. This is the envelope of what we can afford, and this is somehow it's something that is that we know we can't. It doesn't the price performance of both CPUs and disk server isn't steep. It's something that has more or less plateaued. The technology is not as fast as before. One could say Moore's law is dead. Well, probably not yet, but still, we're going in the direction in which we need to think carefully about what we do, because we're surpassing our needs are surpassing the capacity, and especially the money that we can put into this. So how do you overcome these limitations? You either optimize code, that's always good. This is something that we really need to do more. Or we use hybrid computing architecture, so we can reconstruct particles from detector signals more efficiently. If you have a parallelizable problem, use a GPU. There's experiments that are doing it, CMS and LHB especially. You can also refine the algorithm selections to get more of the data that we want. What I'm going to talk about is another method to overcome these limitations, to use the non-standard analysis workflows that will reduce immediate CPU use and storage needs. And this is real-time analysis. And my motivation behind it is that it's, I mentioned it before, it's an interesting time for our field in high-energy physics. We don't really know what to expect from new physics after the Higgs boson, but because we know that there's a number of questions that the standard model doesn't answer, we know that this new physics is going to be somewhere. We have the LHC running now, and the data that we discard will be gone forever. So we really want to make the most of it. So this is the paradigm change that Andy had introduced. We are going from asynchronous data analysis, where you first record and store the data, then you reconstruct and analyze it later, to real-time data analysis. And here you reconstruct and analyze the data as soon as possible after it's read out. And the advantage is that you don't need to keep the entirety of the raw data of the detector. You don't need to remember how each of the channels did, because you already have a derived data format right after the collision event has happened. So you can save only final state information that's much smaller. So you solve the storage problem this way. You cannot go back, so you have to do this real-time data analysis very, very carefully. And in Atlas, we call this trigger level analysis, and we named it like that because it's also a three-letter acronym, TLA. I hope this is funny for people. Going back to the idea here is that at level 1, the hardware trigger, we read enormous amount of data, and we can only output a fixed amount of data out, just thinking about the storage problem. So you can either store a large amount of data for a small number of events, or small amounts of data for many, many events. And here, what is interesting is that we can perform as much analysis as possible in real time because we have a CPU farm there. So let's get the software trigger farm as a real-time analysis facility. Let's do the data analysis as much as possible. Let's do it there. So we reconstruct, we calibrate, we do first pre-selection. This is the analysis in real time that we're talking about. And this was the topic of my ERC starting round that ended last year. You can then save only small amounts of data for many events. So you only keep the final, what we call trigger object. So everything that's been reconstructed and calibrated in the trigger. You know you can't go back, you know you have limited CPU to do this, but it has to be good enough. And you drop the raw data. And in the next data taking, and that's my consolidator grant, we will also be able to save only the interesting parts of the detector. So just shine a spotlight on where we think that there's been an interesting physics object. So for example, what I like is jets of particles. I will just save that part of the detector and all the trigger objects. So this is something that gives me a bit more information. But in this talk, I can't talk about that also because we're still writing the software for it. So let's see if it works. So this is a slide for more data experts because this is the path that this real-time analysis takes. I mentioned that this trigger farm will reconstruct an event, will know what is the content of the event. And it can make a decision, and then only if the decision is positive, then you go to full event reconstruction and you can do the standard data analysis. But in any case, so because this trigger event reconstruction is happening anyway, just do a partial event reconstruction instead of full event reconstruction, put this data in a special analysis stream, and then do the analysis with trigger objects. This saves you a lot of space, and this is something that there's a few numbers thrown out for the different collaborations. There's a for LHCb that has a slightly smaller, is less. Their events are a bit smaller, so you can go from 200 kilobytes where you keep everything. When you keep trigger objects only, you go to 7 kilobytes. And in CMS, that's the other experiment, you go from about 1 megabyte to 10 kilobytes if you do this real-time analysis. And in Atlas, we're going from, at the moment, we're looking at 5 kilobytes versus 1 megabyte. So it really is a lot of a huge saving. You can see it in this this graphical description here. The ball is the size of the full event compared to the size of the trigger level analysis event relative to the full event. And that lets you take a lot more data. So these are the data rates in kilohertz, and the blue is the trigger level analysis, and in yellow is the regular data analysis. There are times in which we can take 20 kilohertz of trigger level analysis, especially at the end of each run, and then really get a lot of the data. For sure, most of it will be background, but in there could be gold. So this huge amount of data comes also with challenges, because software, we need to implement this and deploy at large scale in a system that is very delicate. You don't really want to mess with the trigger system, because if you make a mistake or if you lock it up, then everyone is affected. Performance as well, because a reduced data format might not be good enough for a discovery. We have to make it good enough ourselves. And also the statistical analysis. Once you have such a big background, such small signals, do you really trust what you see? And how do you deal with this in a very robust quantitative way? So I will just show you a few slides on the use case for real-time analysis in dark matter searches. So let's circle back about on the big questions in particle physics. What do we know about this 85% of matter that is dark in the universe, does not emit or absorb light? We can't really see it. We know it's there from astrophysical observations. And the other question is, why should dark matter be a particle? Well, I'm going to go back to our spotlight. Why not? We are made of particles. We're trying to look for particles first. So there's also other explanations for dark matter, but my take is that we need to pursue more or less all of them, because we really don't know what dark matter could be. So I will follow the hypothesis that dark matter is a particle. And there's many hypotheses on what these particles look like. Even though it's an empirical problem in the standard model, there's no explanation for dark matter. There's no only one way to explain it. One of the possible solutions that is guided by how much dark matter is left in the universe, so you can try and infer the properties of the particles that would make it up, is that these dark matter particles are invisible and they can be produced by the Large Hadron Collider. These are called weakly interacting massive particles. So there's also many other experiments that can do this. They all have complementary experimental strategies and inputs, but I'll focus on how to make dark matter in a lab. How do we search for dark matter, for an invisible particle at colliders? We have for sure that to assume some properties of this dark matter particle, and our assumptions is that it does interact with standard model particles, otherwise we can't produce it. So in collisions of protons at the LHC, we can make dark matter particles. These dark matter particles are generally invisible to the detectors, because otherwise we would have seen it also in space. So we have to assume that they are not visible, and there's way to look for invisible particles. But what I'm interested in is the visible signs of this kind of processes. Because this is something that if you've done physics, maybe your particle physics teacher drilled into you. If there's a force, and for dark matter, there should be a force other than gravity to leave as much dark matter around as there is now, then this force needs to have a particle that mediates this force. And the LHC could detect this particle via its decays into visible particles, not just the invisible particles. Because if you can produce this particle, this mediator particle from standard model, then this particle needs also to decay into the same particles it was produced from. Now, the problem is that the mediator decays of the visible particles are nearly indistinguishable from any other physics process that involves the same final state particles. So in this case, it's a practical example where the trigger system is discarding both the signal and the background. Again, we could be missing rare dark matter processes, because if you think about a search for this, a search for the Higgs boson that I showed you at the start, you have the number of events in the x-axis, you have the background, the mass of the two object system. This is the where you want to see a bump. Your background is smooth and your signal is a bump. But if you're discarding both signal and background, then your statistical error, your statistical power is really not good. And this is what the trigger is doing. It's just discarding this part of the curve. So we can't effectively look for rare processes. We don't have the statistical power to do that. But with real-time analysis, so by only recording a small amount of data instead of the full raw event, we can restore the full statistical power for this kind of mediator, dark matter mediator searches. So this is the same distribution. On the y-axis, you have the number of events, the collision events selected. On the x-axis, you have the mass of the new particle, where you expect a new particle. With traditional analysis techniques, we lose statistical power around here. So we would be blind to particles with masses below 1 TeV here. And with the trigger analysis technique, you actually can take all the data and then you can look for a bump over here. Now, there's no bumps here. I can also guarantee that if there was a bump, we would not be able to see it on this scale. You'd really need something. It's an order of one every million. Every 1,000 events, you'd have one signal event. So you wouldn't be able to see it by eye. But trust me, there are no bumps here. So when there's nothing to be seen, then we can place constraints on theory. So we've placed the strongest ever constraints on this dark matter hypothesis with this search. And so finally, I think I have another 10 minutes, 5 to 10 minutes. I wanted to tell you a bit more about what real-time analysis is and what we're doing beyond high energy physics. Because you can imagine that this is not just a problem of high energy physics, the fact that we have too much data. The world is too much data. So I like showing the slide. It's a bit old, but it's for astrophysics, for example, there's two people, one from particle physics and the other from a large scale universe survey, that there's a fire hose of data. And both the LHC and modern astrophysics surveys are data fire hoses. So how to deal with it is actually our problem. But if you think about how connected we are and how much information we generate in our everyday life, we are also data fire hoses. So there's a number of places where we discuss trigger and reconstruction and also real-time analysis in high energy physics and beyond, and I'm leaving some links. So the first one is the HSF, the High Energy Physics Software Foundation. And this is a forum for physicists with interest in software for high energy physics, but also beyond, because we have shared meetings with nuclear physics, accelerator physics, and dark matter experiments, not just LHC people. And we normally write white papers periodically on common software and techniques, but also on the how to go ahead, how to face this huge increase in the data volume that we'll have at when we upgrade the Large Hadron Collider. And this 2021 and 2022, the trigger and reconstruction group has discussed the machine learning for algorithm triggers, heterogeneous architectures, and then even timing detectors. That's a new thing. Many of the participants of this Higgs Software Foundations are also in this cross-field, the Software Institute for Data-Intensive Sciences. It's still a small effort. We're trying to gather funding for making it a bigger thing. So we submitted a cost action across, I think, 15 or 20 countries that are all interested in making this Software Institute a reality. And it is, for sure, it has a bias towards the problems that we're trying to solve in high energy physics, because that's the main core of it. But there is a lot of room for collaboration between computer science and high energy physics, because we as high energy physicists don't have all the solutions ourselves. And along the same line, there's this SWIFT-HEP that is an STFC funded effort led by the University of Manchester that also have a reconstruction and trigger work package. And then coming soon, this is what I'll conclude with, is this European training network called SMARTHEP. We coordinate it. And it's on real-time analysis, machine learning, and hybrid architectures. We call it real-time analysis for science and industry because we're trying to, there are 12 PhD students funded by the European Union that will go and work in different institutes and try to advance real-time analysis and find new solutions for it using machine learning and CPUs, GPUs, and FPGA combinations. And the premise here is that too much data is not only a high energy physics problem. We found out by talking to our friends in industries that time to insight is the key metric for industry. So you want the data and you want right away, you want to know what to do because of the data you've collected. So this is something that it's a problem in finance, it's a problem in self-driving cars, it's a problem in industrial maintenance, and real-time analysis is the shared solution. So what do we want to do here? On the right-hand side, you see a colorful image of who else is involved. But we plan to train 12 PhD students from LHC experiments, computer science, and industry. They are all having PhD topics on real-time analysis and decision-making. And there's 10 students who will be supervised mainly by academic institutes, and 2 that will be employed by companies. It's IBM and Verizon. But all the students will have a mixed academia industry supervision panel, and they will go work at universities if they're industry students, and in industry if they're academic students. And where we're really keen to work together is because there's shared tools and competencies. So the industry have the very advanced tools and also very expensive tools sometimes. And they have also a different scope, but we do have the data. So that's where it's interesting that they really want to work with us, because we have this huge amount of data, and particles have no personal information. So you don't have to go through GDPR problems with that. That's also a fun fact that is interesting, but we're sure that we'll have quite fruitful collaborations out of this network, because we're so keen to work with each other. And this is something that I would never have thought that I would do in my life, doing this kind of technology readiness program. I come from basic science, fundamental science, and then we built together the idea that we need to also to work more with the principles and with the flow and with the different steps that exist in industry, because a lot of the time in high energy physics we tend to throw out a piece of code, hope it works, and then maybe when we go away and do something else, that piece of code remains there. Maybe someone maintains it, maybe not. So we need to be more structured in software development, and we need also to recognize it more. So having this kind of parallels between high energy physics and industry will also help on that side, because after all, if you read here this diagram here, the life cycle of software in high energy physics is not too different from the life cycle of software in industry. And on the bottom is these are all the buzzwords, the things that we want to work together with different between research and all the different industrial partners. So where are we? At the moment, we're still in preparation. So we recruited most of the members of the PhD student cohort. We have 9 students that have accepted their offers. 1 will come to the University of Manchester, and we have this accelerated anomaly detection thesis that will be done in collaboration with CERN, and potentially also with there's a self-driving car company that we will work with in CERN. But we also hope to find more connections within the UK and using the platforms that we also have in the physics department. The students will also start in fall 2022, and we're going to have a kickoff meeting. We're planning to do it at the University of Manchester. We'll see if this happens, because it's there's a lot of visas involved now to come to the UK for the various students. But it should happen. We should have a meeting with all the networks. So I'm throwing out an invitation there if anyone is interested in a joint seminar or presentation of the institute that is hosting the seminars, or even further collaboration. So we'll find a way to get in touch if you're interested. And I was hoping that I could go for a coffee with someone at the end of the seminar, but since I can't now, I'm working from home today. Feel free to drop me an email if you want to talk more, not just about this thing, but about the thing that you're doing, because I'm new at the university, so I want to learn more about others. And I'm very happy to make more connections. And with this, I'll conclude. I hope I've shown you in a good way, not in a necessarily a big science is bad way, that high energy physics is big science in terms of instruments and data volumes. So we need a change of paradigm that from first record then analyzed to almost simultaneous data taking and analysis. And we found that solution in real-time analysis because it leads to enhanced physics inside, better chance of discovering dark matter mediators, for example. And it's also a solution for both science and industry, so we can learn from each other. So I thank you very much for your attention, and I'm happy to take questions. I do not want to drop water on my laptop now. Are people still there? Or have I hope so. I hear some clicking, so at least there's some sign of life. Okay, I'll check the chat now.
We have a hand raised from Hamid Reza.
Yes. Hi, everyone. Do you have my voice?
We can hear you, yes.
I can hear you.
Yes. Thanks for the presentation. I just have some question about the trigger procedure. How do you select the suitable data or events? Do you have any special criteria or just use machine learning techniques?
Well, there's two steps to that. First, you want to combine all the information from the different parts of the detector into one either physics object or event. So an event is made of many physics objects. You get electrons, photons, jets of particles. So you have a mixture of these things. So at that point, when you have when you have all these physics objects, you can have an algorithm that simply asks, is there this physics objects, for example, this electron, and is this electron energetic enough? If that condition is satisfied, then go ahead, keep the event. So that's the simplest way of doing trigger. This is triggering on single objects. You can use machine learning to reconstruct the electrons, for example, but you're not using machine learning to it's a binary condition, a yes or a no. There's also much more complex algorithms for combinations of particles, and that's also the place where you can use machine learning. So you want to combine different tracks in a part of the detector and a number of electrons, or you want to, you can even put a BDT or any kind of inference in the trigger. You can also do that, but I've presented the simple case because most of the time we're working on simple algorithm. And then the machine learning ones are more dedicated because the reason is that the simple algorithms will catch more events that everyone is interested in, while it's more specialized if you go and run your own BDT. Like it will only take the events that you want and maybe not the ones that someone else wants.
Okay, I just want to know that did you implement advanced machine learning such as dimension reduction techniques?
So not yet I mean, as far as I know, and maybe I don't know anything because I've been away for the past few months. These techniques are useful when you want to reduce the complexity also of the machine learning algorithm that you're using, or the algorithm that you're using in general.
Compress the data.
Yeah, so data compression, we can talk about that over coffee, I love it. We're experimenting on data compression with machine learning. But what I was saying is that this is very interesting to make complex algorithms fit on hardware. So these kind of techniques are under study. They're not there yet, but they're being studied because whenever you're working on an electronic device like an FPGA, your memory is limited. So you can't have that. You're much more constrained. So you tend to optimize the network as much as you can in order for it to fit. And this is something that the PhD student will be working with because the people at CERN that the student will be working with are doing exactly this kind of thing. And for the compression, then we work on data compression because that's also another way to solve the storage problem. Although usually when you do data compression with machine learning, it's lossy, and one has to see how much loss you tolerate before you actually can't distinguish a particle from another, or the energy of a particle from, like it's the precision that goes away at that point.
Because there are so many advanced data-driven machine learning techniques for dimension reduction and compression data set. I just want to know that did you test them?
Some of them are tested. So if you fire me off an email, I can send you some literature of what I know, and then you can, if you want, you can make suggestions. So why don't you try this thing, and then that could be interesting.
Okay, because I'm not familiar with the case, but I have worked on large dimension cases, other cases such as data-driven techniques for EVs.
No, that's interesting. Yeah. So yeah, please email me if you want to talk more.
Okay. Thank you very much. Thanks for the presentation. Thank you.
Does anybody else have any further questions at all. I think while if anyone's give people a moment to think, I'm just going to post in the chat our next event. This one's not quite finished, but our next seminar is on the 10th of June. Somewhat different, but talking quite a lot again about machine learning. So this is with Uname O'Reilly. And yeah, that's, as I said, that's on the 10th of June. I'm going to put the link here in the chat if anyone's interested. But yeah, if we haven't got any more questions, then thank you very much, Caterina. And as Caterina was generously saying a number of times, do get in touch. Yeah, if you want to talk about any of the stuff further, yeah, that's what we're doing these seminars for, is kind of make these connections and yeah, and open these discussions. Thank you very much again.
Thanks a lot. So I will send you a copy of the PDF, probably not the animation of the Higgs, but you can click on it. And then I don't know if you want to put it on the, it's actually, I'll put it on a Zenodo, and then I'll send you the link so that everyone can access it.
That'll be wonderful. So yeah, we'll post the video online. I can include a link to the slides there as well.
Okay.
Okay.
Thank you very much for the invitation again, and thanks for the questions.
Yeah, thank you, and thanks everyone for attending. And we'll see you again soon.
Bye bye. Thank you.